Let me welcome you to this lecture. We have now discussed about different allotropes of carbon, and in the last lecture we discussed about graphite as well as about uh, diamond. So during this lecture we will discuss about a very extensive class of allotrope or molecular allotrope of carbon, that is fullerene. So unlike other allotropes of carbon, fullerenes are discrete molecules, and these molecules are essentially of formulation Cn, where n can be anything between 30 to 600. So there are the fullerene molecules or Cn molecules with n equal to 30 to 600. There are indications have been obtained that this up to 600 n can be, and the structure of these molecules are essentially these are again polyhedral clusters, and these clusters are composed of two different types of rings formed by carbon atom. One is pentagonal ring, and the other one is hexagonal ring. So the first member of this fullerene to be discovered was C60, and the structure of this particular molecule is icosahedral in nature. That is, icosahedral symmetry it has, icosahedral, and it resembles the geodesic dome uh, designed by the architect Buckminster Fuller. So Buckminster Fuller uh, was an architect, and he designed a geodesic dome whose structure or whose tectonic uh, shape essentially is identical to the structure of the C60 molecule, and that is why the C60 molecule was initially named as Buckminster Fullerene. So Fullerene, this was the name assigned to the C60 molecule, and that is how these class of uh, these polyhedral clusters formed by pentagonal and hexagonal rings of carbon atom are essentially known as fullerenes. So the initial preparation of fullerene was in 1985. So the group, this Harold Kroto and Ari Smalley. So what they did is that they took graphite and laser blasted the graphite. They irradiated laser beams of high intensity at temperatures above 10,000 degree Celsius. So when they did so, the product they obtained, what they did is that they did something known as mass spectrometry to the product. So when this is a experimental technique which allows one to determine the molecular weight of the compounds, and when they did mass spectrometry, what they found out is that the product contains molecules where which have 40 to 90 carbon atoms. So with uh, all these molecules were present in the product, but the product which was present in highest concentration, or the predominant product that was present in this mixture, was C60 or the Buckminster fullerene. So this was the initial identification of Buckminster fullerene, or preparation of fullerene, and the Proto and Smelly went on to discover the structure of C60 as well, and for this they were awarded the Nobel Prize in Chemistry in the year 1996. So the 1996 Nobel Prize in Chemistry was awarded to Harold Proto and R.A. Smelly, as well as Carl, for discovering the C60, the molecular allotrope of carbon, as well as illustrating the structure of C60. So then, after this, a better preparation methods or bulk preparation method of uh, fullerene was also developed, and in this case, instead of laser blasting graphite at 10,000 degrees Celsius, one can do is one can take graphite, or one can take graphite electrodes and then shoot an electric arc to the on the graphite electrodes at temperatures of 3,500 degrees Celsius, and then one can make a mixture of fullerenes, but where again the concentration of C60 is going to be highest, and one can purify these different fullerenes by chromatography to obtain the different fullerenes in purified form. So different types of fullerenes that have been prepared and as well as characterized apart from C60 are C70, C26, as well as C78, C84, C90. All these types of fullerene molecules have been isolated or in pure form, as well as they have been characterized. So now let us go and look at the structure of these fullerenes before we discuss the chemical reactivity of these fullerene molecules. So in all these fullerene molecules, there are going to be 12 pentagonal rings are going to be present in all of the fullerene molecules. So 12 pentagonal rings are always present. Rings formed by carbon atoms are always present in all the C60 or and higher fullerene molecules. The pentagonal rings that are these 12 pentagonal rings are not adjacent to each other, but the pentagonal rings may be they are adjacent to each other. Apart from these 12 pentagonal rings, there are going to be hexagonal rings are going to be present, and the number of hexagonal rings in a fullerene is equal to Cn by 2 minus 10 hexagonal rings are going to be present. So say for example, in case of C60, if we want to calculate the number of hexagonal rings, here n is equal to 60. So 60 divided by 2 minus 10 is going to be equal to 20 hexagonal rings. So this is how we can calculate the number of pentagonal ring as well as hexagonal ring in any fullerene molecule. And now what we will do is that we will try to draw the structure of C60 molecule and then see how the C60 molecule looks like. So what we can and when you draw this central pentagon, you should make sure that all the edges of the pentagon are equal so that you have a symmetric pentagon here. And then what you do is that one can extend lines from this pentagon at 120 degree from again these lines should be straight and equal in length so that we have a good quality structure. We must ensure that these lines are equal and at 120 degree and we have, now we will draw hexagons here. This is how we draw hexagons. The central pentagon is surrounded by 5 hexagons in this way. So this is how we have drawn. Now we will draw pentagons once again. So this is the place where we have drawn pentagon again, in order to make the pentagon look better. We should readjust it here, over here. Similarly here as well, we should readjust the points somewhat so that we can draw a better looking pentagon over here. So we have now drawn pentagons, and here as well we have to draw a pentagon. Again we readjust the bones here so we can draw a better looking pentagon. Now we will draw hexagons once again. So this is where we will draw hexagon. So this is how we will draw the hexagons. So now we have drawn a one-dimensional picture, but we can also draw the other side of the C60 molecule, because this is only from one side. So for that we will draw dashed bones here. So this is the side which is behind us, and again we should try to make things symmetric so that we end up with a good quality picture here. So let's extend lines from this pentagon, central pentagon, which is behind us, and then draw hexagons once again. So now we will draw pentagons here once again, and this is where we have to draw the pentagons between 2 hexagons. So after that, once we are done with that, we will draw hexagons here. This is where we have to draw another hexagon. So now we will connect the shape, or the shape that is there behind us and the shape that is there in front of us. And for this again we have to see the carbon atoms which are so far divalent, because all the carbon atoms here are essentially coordinated to 3 carbon centers. These are all sp2 hybridized carbon centers. So we will connect these two over here and this over here. Similarly, this will be connected to this one here, and this will be connected over here, this will be connected here. So that we make hexagons essentially. So we have hexagon here, we have hexagon here, we have hexagon here. But this one, we have hexagon over here, and then we have hexagon over here as well, and we have hexagon so this is not correct over here. This should have been drawn in this way here, and similarly this one will go over here. So that is how we can connect. And then now we have completed drawing the C60 molecule. Here we can count that there are 12 pentagonal rings as well as there are 20 hexagonal rings formed by carbon atoms in this C60 molecule. So C60 molecule we have drawn here. So now let us look at the chemical reactivity of this C60 molecule and as well as other fullerene molecules. So because the carbon atoms in C60 are essentially all sp2 hybridized, so the reactions of C60 shows reactions which are typical of olefins, and what we can do, we can do hydrogenation reaction because it is an unsaturated allotrope of carbon. The carbon atoms are sp2 hybridized, and that is why we can do hydrogenation here. And what we can do is that we can start with C60 and then do reaction in liquid ammonia. That is a bead reduction reaction we can do. So with a lithium metal, so bead reduction. You may already know we do for aromatic compounds. And then here, if we do bead reduction, we can prepare polyhydrofullerenes. So hydrogenated fullerenes, and this reaction will essentially yield a mixture of polyhydrofullerenes with C60H18 to C60H36. All these polyhydrofullerenes will be formed, but the major product here is C60H32 is a major product in this reaction. So the hydrogenating agent here in this case is tertiary butanol. So first what you do is you do treatment with lithium. C60 you treat with lithium in liquid ammonia and THF medium, and then after that it is treated with tertiary butanol, which essentially provides the hydrogen atoms, or it is the hydrogenating agent here, and we end up with a mixture of polyhydrofullerenes, among which the C60H32 is the major product here. Now one can do get a C60H36 as the major product or as the exclusive product, by hydrogenation of C60, again by bead reduction. If one uses a different hydrogenating agent, that is 9,10 dihydroanthracene, if one uses is CH2, that is 9,10 dihydroanthracene is used here as the hydrogenating agent, and in that case we end up with C60H36 as the major product here. So what essentially what we see is that like the olefins, here again C60 or fullerenes can also be hydrogenated by using different hydrogenating agents under the brick reduction reaction. So we can as well do oxidation reaction, and treatment of C60 with elemental fluorine at around 70 degrees Celsius for several days will fluorinate only carbon atom here, and so with this carbon atom essentially gets oxidized here to sp3 hybridized carbon atom here instead of sp2 hybridized carbon atom. So we will have C60 F60 is going to be formed within a course of several days when we treat C60 with fluorine at 70 degrees Celsius. So under more harsh condition, that is if we use harsh condition, that is if we do F2 as well as UV light, if we irradiate, and then at around temperature 250 degrees Celsius, we will get instantly C60 F48 is going to be formed as the major product when we do reaction or fluorination reaction under more harsh condition. Instead of running the reaction for several days, the reaction proceeds quickly to give us C60 F48 as the major product. So this is how, apart from this, we can also do chlorination reaction as well as bromination reaction by using typical fluorinating or brominating reagents with C60 molecule. So another important type of reaction that C60 shows is one can also do oxidation that is under basic condition, aerobic oxidation. Under basic condition, sodium hydroxide as well as tetrabutyl ammonium hydroxide. In presence of sodium hydroxide containing tetrabutyl ammonium hydroxide in small quantities, here C60 will undergo aerobic oxidation to give us C60OHN. So these are hydroxylated fullerene, and these are called fullerols. So one can also make fullerols by doing a hydroboration reaction. We have learned about hydroboration reaction in the last while discussing about discussing the boron chemistry. So hydroboration, if we do, that is treatment with B2H6, and in the second step, if we do treat with sodium hydroxide and hydrogen peroxide, then we will again end up with fullerols because we will be hydroxylating the double bonds that are present in the fullerene molecule, and we will end up with this sort of species, polyhydroxylated fullerenes. So these C60 molecules are good oxidizing agents as well, because the reduction potential of the C60 molecule is pretty high, and it can be reduced. C60 can be reduced to C61 minus, C62 minus, C63 minus, C64 minus, C65 minus, as well as C66 minus. So it can be reduced up to C66 minus. It is possible to reduce it, and the species that are formed, or the salts that are formed, we call them as Fullerides. Fullerides are formed when we reduce by using we reduce suitable reducing agents. So now when we treat C60 with say alkali metals, then we can reduce this C60 into M and C60 like this here, and N is equal to 1 for M rubidium and cesium, but N can be anything between 2 to 6 for M sodium, potassium, rubidium, and cesium. So uh, by using different alkali metals as a reducing agent, we can reduce C60, and we can make this sort of Fullerides when we treat fullerene or C60 with different alkali metals. So these molecules have very interesting characteristics, as these molecules, unlike C60, these molecules are very good conductors, and especially the conductivity increases, or the conductivity is highest for M3 C60 here, while M6 C60 is an insulator. M6 C60 is insulator, while M3 C60 is the conductivity for this species is highest. So this essentially tells us that when we react alkali metals with C60, the electron valence, the extra electron that is present in the valence shell of the alkali metal essentially are transferred to the conduction band of the fullerene, which is again formed by the pi cloud or pi electron cloud of these fullerenes, and this conduction band is in fullerene is essentially triply degenerate, or it is, it has, the conduction band has 3 orbitals, so that when we fill 3 electrons here in the conduction band of the fullerene, or in case of M3C60, there are 3 unpaired electrons going to be there in the conduction band, and that is why the electrical conductivity is highest in this case. But when we fill 6 electrons in the conduction band, we do not have any unpaired electron in the conduction band here, which is triply degenerate, and that is why M6C60 is an insulator. Now, two specific Fullerides, that is K3C60 and RB3C60, these are superconductors, because we have 3 electrons here, and the conductivity is very high here, and they do behave as a superconductor with zero resistivity at very low temperature. Of course, around 18 K, these two molecules behave as superconductors. So what we have seen is that we can reduce C60 by using alkali metals, and we can produce such superconducting species when we reduce C60 with potassium or with, say, rubidium. So this essentially brings us to the end of this lecture. What we have learned during this lecture is about a very interesting class of allotrope of carbon, that is fullerene. We have seen that these are extensive series of polyhedral clusters for formulation Cn, where n can be anything between 30 to 600. Of course, the value of n is always an even number that we should remember. And then these clusters are essentially formed by pentagonal as well as hexagonal rings formed by carbon atoms. We have also looked at the initial synthetic procedure for C60 molecule, as well as we have seen the later developed bulk preparation method of C60, which essentially allowed for isolation of pure C60 as well as other fullerene molecules like C70 or up to C90. Now we have also looked at the structure of these fullerene molecules, and we have seen that in all of these fullerene molecules there are 12 pentagonal rings, as well as there are n by 2 minus 10 hexagonal rings. So in case of C60 we have 12 pentagonal rings and there are 20 hexagonal rings. We have also drawn the structure of C60 molecule in the three-dimensional structure of C60 molecules, and we have seen these 12 pentagonal as well as 20 hexagonal rings, how we can draw this C60 molecule. Then we have finally looked at some of the chemical reactivity of this C60 molecule. We have seen that it shows typical reactions shown by olefins, so that it can be hydrogenated under big reduction conditions, and one can make polyhydro fullerenes by using this. And then after that we have seen that it can also be oxidized to by fluorine, elemental fluorine. It gives fullerenes or perfluorofullerenes, that is C60. F60 can be prepared under when we react C60 with fluorine at under 70 degrees Celsius for several days, and then we can also do fluorination under harsh conditions. And then in that case, when we do treat C60 with fluorine under UV light irradiation and at 250 degrees Celsius, we isolate C60F48 as the major product there. And then we have seen that we can also do chlorination as well as bromination by using conventional chlorinating as well as brominating reagents. Then we can also hydroxylate C60 by using aerobic oxidation as well as by doing hydroboration reaction. Then finally we have looked at that how we can the oxidizing capacity or oxidating nature of these fullerenes, because their reduction potentials are pretty high, and because of that they can reduce the alkali metals, they can oxidize the alkali metals and they themselves get reduced, and we can reduce up to C66 negative reduction is possible. So then we have also seen the interesting electrical behavior of these C60 or fullerides, because the electrical conductivity increases up to C63 negative, but then after that, if you reduce further, then the conductivity decreases. That is because when we feel electrons in the conduction band of this fullerene, which is triply degenerate, then after when we feel 6 electrons in the conduction band, then there are no unpaired electrons left in the conduction band, and that is why the M3C60 essentially M6 C60 behaves as an insulator, while M3C60 the conductivity is highest. And two of these examples, that is K3C60 and RV3C60, they behave as superconductors as their resistivity is 0 at a specific temperature. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.